thank you very much for coming. It's my pleasure to introduce Amar Bhatt. I've known Amar for at least 3 years. Initially, I think when you were maybe a second-year student, and you were interested in robotics and started getting into our automated wheelchair we call MilPet now. And so now actually we have Jacob and Masika in the back there who are the new parents of MilPet. And so it's kind of passed on from generation to generation. And so he's been very successful in 2 publications, another one hopefully coming from that, from those efforts. He's TA'd in so many classes, won TA awards. It's unusual for me to have a list just to make sure I understand, because he's got so many accolades. I think it's important that maybe we some of these, because they're very unusual, very amazing. So in addition to the great stuff you've done as TAs and TA awards, you were on the RIT Presidential Search Committee, very unusual. KGCOE Senator, Student Government Vice President, and just recently, this past semester, he got the Excellence in Student Life Award, which is very amazing. His name is forever embossed on the RIT campus in the Fireside Lounge. And actually, I saw a photo of it in the SIU as I walked by, so that's pretty amazing. And so as part of that, he got to go to President Dessler's house, and I got to join him for that. And I was like, wow, I've never been here before. He's like, oh, I've been here a couple times already. You know, who is this guy? He has so many accomplishments. And on top of that, just a stellar GPA, which is pretty amazing. So in any case, on this particular research on reinforcement learning, like anything else, Amar goes after big challenges. This is definitely not a field of my expertise. Thanks for Dr. Kanan for helping out and steering us in the right direction. And thank you all to the committee, and thank you everybody else for coming. Mr. Bhatt, thank you for coming. We're very proud of your son. I'm sure you are as well. So without further ado, Amar.
Thank you. Thank you for those kind words, Secretary Chen. So yeah, like I said, I'm Amar Bhatt, and this is my thesis defense, and my thesis title is Teaching Agents with Deep Apprenticeship Learning. Just a side note, there's coffee and donuts in the back, so help yourself. Get up. I don't think it's super formal. First of all, I'd like to thank my friends, family, faculty who showed up, especially my committee. So I have a fairly large committee from all different disciplines. So thank you to Dr. Petrucci, who's my advisor, Dr. Sahin, Dr. Islani, Dr. Kanad, and Professor Beata. So really quickly, kind of just going through my agenda. Oops, sorry. I'm going to really quickly go over what reinforcement learning is, because that's kind of the backbone of my research. You really need to understand that. Then we're going to go into apprenticeship learning, which is what my research was geared towards. I'm going to go through my problem statement, some of my novel contributions, the algorithms, methodologies I use, my test environment, and then to conclude with my results. All right, so getting into reinforcement learning. So what is reinforcement learning? Living creatures, just like humans, animals, learn through trials of rewards and punishments, right? So that's what reinforcement learning is. It's basically some type of creature or some type of system or agent randomly navigating its environment to learn how to best interact with its environment. So if you think about when you were younger and you touched the hot stove and you got burned, you're like, oh, that's a bad thing. That hurt me, so I'm not going to do that again. Again, that's kind of how reinforcement learning works. It tries an action, either gets reward or punishment, and decides whether it should do that action again. Reinforcement learning is good for solving Markov decision problems, or MDPs. Basically, the MDP, basically the rule of it says the probability of going to one state to the next state only depends on your current state. Nothing previous, nothing, things that you've observed in the past don't matter. It's only where you currently are to get to your next state. And then unlike supervised learning, it doesn't require ground truth data. So like I said, it really depends on just randomly exploring your environment and trying to look at everywhere you can go and all the actions you can possibly take. You don't really need ground truth data for this. So how does it work? You have an agent, which could be a car, a robot, a system that's situated in some environment at some state. So a state can be the location of an agent, the proximity of the agent to certain obstacles of the goal, the current health of the agent, the time that they're in the environment, or really any combination of these features. And basically anything that describes where the agent is in any given time, at any given point in time. An environment can be a maze, a workspace, field, a road, anything, any type of thing that you're trying to learn how to navigate or interact with. So an agent in an environment at a state can perform some type of action. So that could be moving up, down, left, right, opening a door, throwing a ball. All actions will result in some type of reward, and the action will always result in some type of state transition. So to get from one state to another state, you need to perform some type of action. So you have the set of states, and you have a set of actions, and you're trying to learn some type of policy. And basically what a policy means is I'm at a certain state, what action do I want to take to get to my goal, or to complete the task I'm trying to complete? And you do this over several iterations. So one iteration of a complete game is called an episode. An episode always ends in a terminal state. So you start at one state and you end in the goal, or you end falling off a cliff, or you die, or whatever. That's one cycle. To learn, an agent needs to do several iterations. Just like when we were younger and we were trying to learn, we had to do a certain task multiple times before it really understood how it worked. So rewards. Like I said, actions always result in some type of reward. So you always get a reward from, when you go from one state and take an action to another state, you get an immediate reward. You also want to consider future rewards, right? So the whole point of reinforced learning is to complete some type of task or get to a goal. So you want to consider, well, what are some rewards, like after I take this action, how good is this action to get me to where I need to go, or to complete the task I need to complete? So we have to consider the total reward, which is big R of T. And basically that's the sum of little rewards for every state action that you take over a given episode. So usually these future rewards are discounted by some type of gamma factor between 0 and 1. And basically what this means is we want to highly weight immediate states. So I'm in a current state, and the next state I really want to say, like, that's really important. But future states I want to say, they're not so important. They'll be important later as I get closer to them, but I don't really need to consider them as of right now. So Q learning is one of the most popular forms of reinforcement learning. It comes off the branch of temporal difference learning, which basically says it kind of learns over time. And it uses estimated equations to learn about an environment over numerous iterations. So I'm going to go through some examples and kind of explanation of Q learning. That's kind of like, this is what's been used in literature and research. It's the most popular reinforcement learning algorithm. So for each state action pair, there exists some type of Q value. And this Q value basically says, how good is how good is it to take an action in a certain state that I'm in? It also says, if I was to take this action in the state, what is the potential reward I can get, or the potential value I can get if I continue optimally from this point on? If I say I continue and I take the best actions that I've learned from this point on. The Q values rewards are represented as tables of states, which are rows, and actions are columns. I'll go through an example of Q learning to highlight that. And the goal of Q learning is to learn a policy, right? So the policy is basically, I'm at a certain state, which action has the best Q value, and I'm going to take that action. So over several iterations, that Q value is going to become accurate enough where you can say, oh, I'm in a certain state, this action has the highest Q value, I'm going to take this action. If you keep doing that, you're going to end up getting to your goal or completing the task you're trying to complete. There's only one really problem to this. How do we estimate this final reward or final Q value if we only know the current state in action, right? So like in the beginning, you don't know what your Q values are. That's the whole point of this, the whole algorithm, is that you really don't know. So that's where we come with the Bellman equations, and this is the approximation. So looking only one state ahead, you can estimate the Q values for state action pairs. So over several iterations, obviously these estimations will become the truth. So that's why we have to do many episodes. And so if you look here, this is what the Bellman equation looks like. So the Q value for a certain state and action pair is equal to the immediate reward you get from being in that state and taking that action, plus the discounted factor, this gamma value, of the maximum Q value of the next state that you're going to be in. And so if you do this over a certain amount of times, like I said, these will eventually become true. In the beginning, obviously these Q values will be very inaccurate, and over time they'll become more accurate. So to iterate, so you say, well, I want to update my Q value for a certain state in action because I observe something new. And basically that equation is the current value plus this alpha, which is the learning rate of how fast you want your algorithm to learn, plus this Bellman equation, like we see up here, minus the current Q value. So over time, this term right here will end up being 0 as you learn proper Q values. And that's at that point you can say, okay, well, my Q values have saturated, I've learned everything I need to know, and I can stop learning. And that's why you can stop iterating over your environment. So this is basically just a high-level algorithm. For every episode, you start at a random state, and while the state is in a terminal state, while you're not at the goal or while you didn't complete the task, you're going to choose some type of action using a policy. You're going to take that action, you're going to observe the immediate reward you get and the next state, and then you're going to update the Q values, and you're going to continue that until the episode is done, and for every episode that you want to iterate over. So we're going to go through a really quick example. So let's say you're in a 4-room house and you're really hungry. That's usually the case in my house. So your goal is to get to the kitchen from any room in the house. And basically your only action is to move through any door. So you set up your Q table. You say, okay, well, all my state transitions are 0. We don't know what the Q value is, so we're going to initialize them to 0. We're going to say our reward is basically saying that, If I go from A to B, I get a reward of 0. You really can't stay in the same state unless you're in the terminal state. And then if you see here, if I go from C to D, which is from the living room to the kitchen, I get a reward of 100. So go through one iteration, and I'll show you how it kind of can, the Q value saturate towards the end. So we'd say our gamma value is 0.9, so we really want to highly weight future states. And let's say we start in the bedroom, and we transition to the living room. So using the Bellman equation, we say our immediate reward is 0, times this gamma, times the maximum reward we can get from state C, which is also 0. So we get an update of 0. Doesn't really do anything. Now we're in the living room, and we say we're going to transition to state D, which is the kitchen. And we say, okay, well, the immediate reward of going from state C to state D is 100, times gamma of the maximum value, of the maximum Q value that D has, again, which is 0. So the Q value from going from state C to state D is 100. And the same thing, if you're in the kitchen and you stay in the kitchen, you're going to get a Q value of 100. So you go through a number of iterations, and you start in random areas, and every time you hit a terminal state, you just start in a random state, and you start over, and you keep iterating. And at the end, you basically have a Q table that represents some type of policy. So like I said, the policy is at a certain state, which action has the highest Q value, and that's the action I'm going to take. So we see here, if I'm in the bedroom, I want to go to the living room, and we see that that has the highest Q value. For the bathroom, I want to go to the bedroom, because that takes me towards the kitchen. From the living room, I want to go to the kitchen, and in the kitchen, I want to stay in the kitchen, as those have the highest Q values. So this was a small example, and there's some other extra considerations you have to consider when doing Q learning. So exploration versus exploitation. Exploration is choosing random actions to explore your environment, to find different paths and different different states and different actions you can do in those states. And exploitation is saying, I'm not going to choose random action. I'm going to do what works. I'm going to do what I've learned and how I've been taught. So how do you determine this balance between exploitation and exploration, right? So if you do only exploitation in the beginning, you're not going to get anywhere because all your Q values are 0. So you usually you use this algorithm called epsilon greedy, which basically says with probability epsilon, you're going to choose a random action. Otherwise, you're going to choose a learned action. So in the beginning of while your agent is learning, the epsilon is a very large value, either 1.0 or 0.9, and it says, I'm going to choose a bunch of random actions in the beginning to try to set all my Q values. As time goes on, as I go through my episodes, my iterations, I'm going to start slowly decrease the epsilon value and say, well, now that I've learned all these Q values, let's do what works. Let's start exploiting some paths that I've already discovered work. And that's how you balance that. Also with Q learning, you need to know the reward structure of your environment. You need to know the reward you get from going from one state to another, and the reward of your goal, and the reward of not getting to your goal. Also, let's say you have a large state space. Let's say we only had 4 states here. Let's say you have 100 or 1,000 or 10,000 states. These Q tables can become really, really big. And basically, these tables would take too much memory. It's really insufficient. So this type of Q learning is really inscalable. It doesn't really scale well to larger problems. So one way to solve that is using neural networks. And we can use a neural network to replace the Q table entirely to estimate the state action Q value and basically approximate that. So let's say we have this game, Atari Breakout, and let's say we just want to learn from raw pixel data, right? So let's say we pre-process this image to an 84 by 84 image and make it grayscale, so it's going from 0 to 255. So if we were to solve this using traditional Q learning with the Q table, that would result in 256 to the power of 7,056 states, which is crazy. You really can't represent that in a table well and be efficient. Also, using a neural network, it's really good for feature learning. You don't have to tell a neural network, hey, focus on this in the image or focus on this in the state. The neural network is going to learn what it needs to focus on to get the task done. So using deep convolutional neural networks, especially in these using raw pixel data, we can learn from this data. So I'm going to go through some related works. Really, my research is all about learning from raw pixel data. So I'm going to go through some Q learning methodologies that use raw pixel data. So one of the most famous, and many people have heard of it, is DeepQ network, which was introduced by Google DeepMind. And basically, they created the DeepQ network to solve Atari games. And they made 2 really significant changes from the traditional Q network. One was experience replay. And basically, that means instead of feeding into the network sequential steps the agent takes, it feeds in random batches of experience. So if it feeds in sequential steps, the neural networks tend to converge to a local minima. So you need to really randomize and make sure that that you remove the correlation between all the data that you're feeding into a neural network. So as the agent explores its environment, it stores these into experiences of the current state it's in, the action it took, the state it ended up in, and the reward it received. And you limit this replay buffer, is what we call it. So you limit that and you say, well, at the beginning, all the experiences I have are probably bad. They're probably not good experiences, but towards the end, they're really good. So we want to get rid of the old experiences and replace them with new experiences. And again, like I said, this removes the correlation. The next change they made was the target queue network, which was used for calculations. So basically, queue updates, as you can see, the updates for them can be really large, especially in the beginning. So you initialize everything to 0. These updates can be crazy, really, really large, and it can cause network to diverge. So for using a target queue network, you have your primary queue network and you have a target queue network. The primary network updates at every iteration. After, let's say, 10 iterations, it takes the weights that it learns and passes it over the target queue network, which is usually those weights are much more stable and they don't change as frequently. And you use the target queue network in your calculations. So as you can see here, you want to minimize this loss function, which is basically the Bellman equation that we saw. So going through the architecture, the deep queue networks have 3 convolutional layers and 2 fully connected layers. It takes an input of an 84 by 84 image, so like I said, it takes these Atari games, pre-processes them to an 84 by 84 image, and makes them grayscale. And it feeds in 4 frames at a time. And feeding in 4 frames at a time does a couple of things. One, it gives the network an idea of what motion. So if we think about the game Breakout, it basically gives the game an idea of what direction the ball is going in. You really can't tell that from 1 frame, but if you give it multiple frames, it can say, oh, the ball is going in this general direction. It also is more efficient for the network. And the last thing, it basically says, if you think about Atari games, right, over 4 frames, especially in Breakout, the ball doesn't really move much. So we're saying these 4 frames represent one state. Instead of saying each one of these frames that look exactly the same or identical are different states, we're saying these 4 frames together are one state. And it helps the system learn a lot better. It comes out, so you feed into this network this 84 by 84 by 4 input, and you get a Q value for every action you can possibly take. In Atari, you can move up, down, left, right in all the cardinal directions. You can also press a button, and you can also just do nothing. So each one of these actions, all 18 actions, will have a Q value. You basically choose the Q value that has the highest value. So when they compare this to several Atari games, this line basically represents at human level. So humans perform the same. So anything above this, the game beat humans. And it beat humans on a number of different games, especially in Breakout. And Breakout is very interesting. There's a strategy that not many humans even know. And one of the strategies is break the side walls so the ball gets to the top, basically can freely hit the bricks without you having to control anything. And this DQN network actually learned that strategy, which is pretty cool. So Google DeepMind said, okay, we're not going to stop there. We see that our Q values, they're unstable, they diverge a lot. We didn't really do so great in some games. So how can we make that better? And one modification of this was to use the separate target Q network and basically separate the action choice from the Q value generation. So it uses the primary network to say, okay, in my next state, what's the best action I can take? What's the highest Q value? All right, I'm going to choose that action. Now, I'm going to see what my target Q network says that Q value is. And I'm going to use that for my calculations. So again, like I said, it decouples the action choice from the Q value. And if we use the primary network to estimate the Q values, this Q value changes over time. Like it changes very rapidly after every iteration. So it reduces the overestimation of these Q values because we're saying the target Q network updates these Q values every couple of iterations. So it's going to be more accurate and a little bit more stable. And like I said, it brings more stability to the network. And when they tested it on the Atari games and compared it to the DQN, it showed that it beat the DQN in many games and was able to solve a lot of the games that the DQN couldn't. So they said, okay, well, we're not going to stop there. What's another modification we can make to this network? And this is dueling deep Q networks. And this is probably the most robust network in the deep Q learning space. It's used in a lot of research. It's kind of become the standard, this type of network. So it uses the same architecture as the DQN and the double DQN. And it basically says, the Q value represents how beneficial it is to take an action in a state. Okay, well that makes sense. But why do we want to characterize the value of a state by the action you take in it? So let's say you're in an environment or a world that has a red zone and a green zone. It's really good to be in the green zone. It's really bad to be in the red zone. So if you're in the green zone and you say, what is the value of being in the state? Why characterize it saying the value of the state, if I go up or down or left or right, is different. Being in the green state is a good thing. So we want to split up the value of being in that state versus the advantage of taking an action from that value. So that's what we do. We split it into 2 values, the value of being in the state, how good it is to be in the given state, and the advantage of taking an action compared to other possible actions. And then you add them up at the end. So basically it's saying the same thing, but we're splitting up how we're calculating those 2 things. So this, when compared to the double DQN network, this is the percent of how much better it was than double DQN network on these Atari games. And as you can see, for most of the Atari games, it blew the double DQN out of the water. So they said, okay, well, considering the state and the action choice as different things really did help. So the final modification that they tried was saying, okay, well, a lot of these Atari games are sequential, right? You take one step and you take another step, and what better way of representing sequential data and how it works than using a recurrent neural network or an LSTM. Also, if you think about like Breakout, you see the whole state space in one frame. You see all the bricks, you see where the ball is, you see where your paddle is, and that's fine. But there's also games where you turn a corner and the whole world changes, or you leave or it's a side-scrolling game where you leave the screen and something else happens. And those are called partially observable MDPs, and the DQNs do really bad at those games. So things like Frostbite and Double Dunk, where the environment can change based on where you are on the screen or if you turn a corner or anything like that. So you need to keep track of these sequences and past decisions to make sure that you're still following the right path. And that's where the deep recurrent queue network really helps to solve. So it basically adds an LSTM layer right before it does the value and the action separation, just like in the dueling network. And when compared to the DQN, it does okay in some games. It beats the DQN in some games, and for the most part, it either parallels or does much worse than the DQN. And a lot of the reason is, like I said, reinforcement learning follows the rules of MDP. Your current state, your next state only depends on the current state you're in, nothing before that. And this kind of breaks that rule. So now I'm going to go into apprenticeship learning, which is really what my research is, and you're going to see how the reinforcement learning aspect of this folds into it. So what is apprenticeship learning? It's basically inverse reinforcement learning. So what if you don't know the reward or cost function of your system, right? So in the Atari games, you know your score, you know the reward you're going to get. What if you don't know that? Like, how do you solve the system? How do you use these Bellman equations to figure out where you need to go if you don't know what reward you're going to get or how you're supposed to interact with your environment? So complex systems such as like driving or making a robot walk, they might not have these simple cost functions to minimize. So if you imagine when you're driving, you're taking in all these features from your environment. Is the light red? Is the car next to me too close? Do I have to make a turn? And you're also taking all these features in from what you're doing in the car itself. Especially if you're using shift stick, am I holding the clutch? Am I shifting properly? Am I turning the steering wheel? Am I holding the steering wheel right? So how do you take all those features and combine them and say, okay, what I'm doing is good or what I'm doing is bad? You really can't. So the best way to do that, just like as we all humans learn, we learn through an expert doing them with us, right? So we usually sit in the car with our dad or mom, they tell us how to do something, and we learn how they do things, and then eventually we learn our own experiences and we learn how to do that back. So we want to create a system that can learn this optimal policy or reward function by watching an expert or watching somebody do a demonstration of the task or goal we're trying to complete. So just to kind of highlight the difference between reinforcement learning and apprenticeship learning, reinforcement learning, you know the reward structure, you pass into this reinforcement learning algorithm, and you have your environment, and out comes an optimal policy. For apprenticeship learning, you have these expert demonstrations or trajectories or whatever, and you try to extract the optimal policy. So you might not know exactly what the optimal policy is, you only know what the policy is based on what you see the expert do. You pass in this inverse reinforcement learning algorithm or apprenticeship learning algorithm, and out comes a reward function. And this reward function explains what the expert did, but it might not be exactly what the expert followed. But it generally says, if you use this reward function, you're going to perform similar to how the expert did it. So like I said, you first need to extract a policy from an expert set of demonstrations, which isn't easy. Then you need to learn a reward structure from that extracted policy. And so this has been done using expert trajectories. So let's say you have a maze, and you see an expert solve this maze in a bunch of different ways. You're like, okay, well in this particular maze, the expert went through this coordinate, this coordinate, this coordinate, this coordinate to get to the goal. Like, okay, great. So you have a bunch of data from the expert what they did, and you say, okay, well, the expert visited this part of the maze a lot. The expert didn't visit this part of the maze a lot. All right, so my policy is generally, let's go to the parts where the expert visited the most. So that's great, and it worked well, but that doesn't really scale to diverse environments. Let's say the maze changes. Let's say the expert is solving different mazes, and now you just have to solve just a general maze. The task is still the same. You're still solving a maze. You're going from one state to the goal. But if you do the state visitation frequency saying that, oh, the expert was in this part of the maze the most, your maze is different. You really didn't learn what the expert did. You're just kind of copying what the expert was. And you're not trying to mimic what the expert's doing. You're trying to learn how to do a task from the expert. And also in this, there's not many raw pixel solutions to apprenticeship learning like there is in reinforcement learning. There's no Atari data set that says, let's learn Atari games using apprenticeship learning, again, because you have the reward structure. So that's kind of a challenge. And again, like I said, my research is mostly on how do you learn from raw pixel data. So I'm going to go through some related works that basically do that. So the deep apprenticeship learning is probably one of the only true apprenticeship learning algorithms and networks that take raw pixel data without a reward structure and try to learn from it. So this, again, this architecture used Atari. The algorithm, again, doesn't use a neural network or anything, did fairly well. And the DAL didn't do much better than the SARSA and did much worse than the human learning. So while the results weren't great, this is the first implementation, probably the only implementation that has raw pixels. It's a raw pixel solution for deep apprenticeship learning. So this paper, which is Deep Q learning from demonstrations, again, this is Google DeepMind again. They didn't give up with reinforcement learning. They wanted to get into, well, how can they learn from demonstrations? This paper came out in late April, so very recently. And this is, again, it's kind of showing that this type of research isn't really being done by a lot of people, and it's still, there's a lot of new things coming in almost every week. So basically what they're saying, I want to utilize DQNs with transfer learning. So first I'm going to learn from expert demonstrations, an expert playing a bunch of Atari games. I'm going to train my network on that, and then I'm going to train from experience like we talked about before. So they still use the experience replay, but they use shared experience replay, which means that 10% of the experiences I learn from are from my expert, and 90% are from my agent. So basically saying, okay, throughout time, just like humans, like if somebody tells you how to do something, that experience and that memory follows you as you make decisions in the future. So they showed that one, this helped the networks learn faster, and that it beat a lot of the traditional DQN networks. So when compared to double DQNs, it did really well in some games and got really close to being double DQN in other games. Unfortunately for this, you still need another reward structure. They still use Bellman equations. You still need to know the reward you're going to get from going from one state to another. They still feed in the score from the Atari game into the system.
What was imitation?
Imitation is just basically just straight supervised learning.
Okay.
Basically saying this is a statement this action I took and just classify. So my problem statement. Like I said, I want to teach a system to perform a task given only videos of an expert doing the task well and optimally. So some examples of where this could be used is, let's say you have a robotic surgical system, and that's really where my field is going, and you want to learn how to make proper cuts on doing some type of surgery. So you give the system, you say, okay, well, watch all these videos of a surgeon making cuts. There's I have 100 surgeons making cuts on a bunch of different patients. Learn how to make the optimal cut now. Okay, so that's great. You don't know what the reward structure is. You don't know what the surgeon's thinking. But by watching the surgeon, can you extract a policy that says, and this type of person and this type of what I'm seeing, this is the type of cut I'm going to make. Also, it can be used to teach factory robots to learn how to assemble a part, and also autonomous vehicles to learn how to drive. So I do this testing two things: task completion versus task understanding. Task completion measures how well a system can complete a specific task. So let's say we have a robot, basically a pick-and-place robot that picks up a part and places a part in a box. So this robot just watches a bunch of experts just picking up a part and putting it in a box. Can the system learn just by that, just from doing that one simple task where the environment doesn't change and the task doesn't change? Task understanding measures how well a system can generalize the task needing to be completed. So let's say that same robot has to pick up a part, orient it in the right way, and then place it in the correct box. Right? So the task doesn't change, but the environment can change. Every part could be oriented in a different way. The boxes can be in different locations. You have to always put it in a different box. So how well can the system generalize? And as you can see, task understanding is a much harder problem to solve in apprenticeship learning than is task completion. So some of my novel contributions and things I tried. The first and probably the most important is reward abstraction. This is basically saying it's a task level abstraction of rewards. Like I said in apprenticeship learning, you don't know the reward structure of your environment, of your system, or what your agent's doing, but that really limits you. That really limits you. So as you can see, like in reinforcement learning, right? Using the DQN networks did really well. Well, why can't we use the same concepts in apprenticeship learning? So instead of saying, okay, for every step I get this certain reward, I abstract it to a task level performance. So I say, okay, if you complete the task, you get a positive reward. If you don't complete the task, you get a negative reward. All the other intermediate rewards are 0. So that allowed me to use Bellman equations as well as the DQN networks, as I'll show it later. And then from that came other modifications, so scheduled shared experience replay. So as I said, the Google Deep Network, the last one I showed, basically combined expert experiences and agent experiences. That's great. What if I said, okay, while the agent's learning, right in the beginning, most of its experience, let's say 90% of its experiences are from the expert. And then as your time goes on, you decrease that, and more of the experiences are from what the agent experiences. So that's kind of like, you know, how we learn as children, right? So your parents tell you, oh, do this task this way and this way and that way. And you're like, okay. And as you do those tasks, your parents' memories, your parents' experience, what they taught you is first and foremost in your mind. Then, as you keep doing the task, you do it your own way, and you learn your own experiences, those memories start slowly fading, and you start learning it your own way. And that's exactly what this is. So basically, you have a guide throughout the learning process of an agent that slowly starts fading away, but starts out really strong. The target queue network implementation, like I said, the target queue network gives stability to the DQN network. That's kind of a method I had to use when I used the DQN network. The dueling DQN, like I said, was the most robust DQ network. And I said, well, it did amazing in reinforcement learning. Let's see how well it does in apprenticeship learning. Because the concept of splitting the value of being in a state and the advantage of taking an action did really well. So I can only assume that it'll do really well in apprenticeship learning. And then deeper current queue networks, it didn't do so well in reinforcement learning because, you know, it kind of breaks the rules of what reinforcement learning does. But I said, well, let's compare it in apprenticeship learning and see how well it does. And a lot of these apprenticeship learning papers that you read, a lot of their future work says, you know, I want to try this with recurrent network. I think this would work well with recurrent network because it's a sequential problem and it would work well. So I was like, okay, well, let's put it to the test and see if it actually does do well. So some of my algorithms methodologies, I tested 9 networks. So the first network is the DAL, the deep apprenticeship learning, without any modifications, because that's the only really pure solution as a deep apprenticeship learning model. So I want to say, well, let's see how well this does in my tests. Then I say, let's do the deep apprenticeship learning without a pooling layer. Let's say, let's not remove the spatial information, see if it does better if I say, let's remove this pooling layer. Then I say, let's do the deep apprenticeship learning with transfer learning. So let's say, after we train the DAQN on expert data, let's take the weights that we learned and initialize DARN before it even starts learning and see how well it does, right? You're still feeding it the same information, you're still feeding it the same state images, and it's almost learning the same exact way. So let's keep the same weights. Then I say, okay, well, we know the Bellman equations work really well in reinforcement learning. Let's apply that to apprenticeship learning. And so we use the DAL with Bellman equations, and this is where we need to use reward abstraction. We don't know the reward from every state to state transition, but we know if the agent can finish the task or doesn't finish the task. The next is I use the deep queue network in apprenticeship learning. So I call it deep queue network apprenticeship learning. So I use the DQN architecture with shared experience replay and the DQN architecture with scheduled shared experience replay. I do the same for the dueling DQN, and as well as for the deeper current queue network as well. And I test all those to see how well they do. So for the deep queue network apprenticeship learning, I had to create my own algorithm, my own loss function to really model this. So I say the loss is basically a weighted sum of this temporal difference, or this queue learning update, plus this weighted value of basically the cross softmax entropy error of what action I predicted should be and the action the expert actually took. Right? So again, my Q target is this Bellman equation, where this RSA is task completion. So in the middle, if it's at the end of the state, if it's at a terminal state and it gets to the goal, it gets a positive reward. If it hits a wall or falls off a cliff, it gets a negative reward. Otherwise, it's 0. And QSA is the output of the network for state S and action A. The action predicted is the action found by the network to have the highest value for a particular state, and the action AE is the action the expert took. And so lambda 1 and lambda 2 are hard parameters, and they add together to equal 1. And during agent training, so during expert training, lambda 1 and lambda 2 are both set. For agent training, since we don't know what the expert would have done, we say the lambda 2 is 0 and the lambda 1 is 1. So you're only learning on the Bellman update equation. So this is the algorithm. I'm not going to step through it line by line, but at the beginning, you first train on expert data, and then you say, okay, well now we're going to train the agent, and right here is where you generate the agent experiences, and on this part of the agent training is where you combine the expert data and the agent data, and you learn on batches of those. So my test environment, one of the challenges of apprenticeship learning is that there's really no data sets that exist that have both expert demonstration data and a simulation environment for my agent to learn it. And so basically I had to create one from scratch. And so unfortunately that makes it a much tougher problem because it's very hard to benchmark. But I basically need this data set to be easily testable, easy to configure, and easy to generate and simulate data. So I created Maze World. Maze World is 100 pixel by 100 pixel images of 10 by 10 mazes. And so I generate my expert data, basically the mazes being solved using Dijkstra's algorithm. So as you can see here, this is basically what one data set of an expert would be. It's basically an expert starting a random location and getting to the goal. For random data, and if you can remember, the deep apprenticeship reward network in the deep apprenticeship learning architecture needed just random state-to-state transitions, so it can generalize in different states that it hadn't seen. So basically that's all I do. I just generate these same mazes with an agent starting around location and going to a state using some type of action. So for task completion, I test on the same exact maze with the agent starting in different locations. And where the agent starts is important because if you see, as you can see here, the agent's is right next to the goal. The goal is represented by this light gray square. So some of them are really easy to solve, some of them are kind of hard to solve, and others are really hard to solve. So I have an even distribution of really easy to really hard mazes to solve. I do the same thing for task understanding, but for task understanding, the maze changes. So we say, how well does it generalize to the task that needs to be completed? And again, some of them are really easy, some of them are really hard, and some of them are right in between. So I analyze how well my networks do with this data set with two metrics. Completed tests, which is the number of mazes solved from the test set, and correct action prediction. The percentage of correct actions predicted over the total number of actions that could be, or the total number of correct actions that could have been predicted in the test set. So into my results and some of my conclusions. So for task completion, again, these 8 networks here are novel solutions, basically things that haven't been tried. And the first is just the deep apprenticeship learning without any modifications. So for the deep apprenticeship learning, removing the pooling layer in the DAL didn't really result in better performance. And basically, it's really showing this architecture is too simple to characterize input images anyways. It's not as robust as the DQN networks. We showed an increase, so when I said, okay, let's try transfer loading. When I made that modification, we did see an increase. And this gave me proof that saying in the DQN networks that I had, and the DeepQ network apprenticeship learning, that I could use transfer learning from when I learned from an expert into how I learned from an agent. So it gave me proof that I could do that. Adding the Bellman equations, again, showed a slight increase over the original network. But the instability to Q learning kind of caused it to diverge quickly. But it did show that the Bellman equations did really work well in this apprenticeship learning model with the reward abstraction. And kind of in conclusion with the task completion, this network is really kind of too simple and really can't be expanded to complex environments. And that was kind of shown in the research when their network didn't really do much better than just a Q table version of apprenticeship learning. So for the DQN networks, the DQN architecture, as been shown when it solved for Atari games, can learn from raw pixel inputs really, really well. The network is made for them. And scheduled shared experience proved to be an enhancement over just using shared experience data. So that was again, a novel contribution of adding the scheduled shared experience of having a guide throughout the agent's life showed to be a huge benefit. The dueling DQN, as robust as it was in reinforced learning, showed to be just as robust in apprenticeship learning for task completion. And the DRQN performed the worst. Again, kind of expected. It doesn't fare well in non-partially observable MDPs. Also, it kind of breaks the rules of reinforcement learning. So for task understanding, and this is a much harder problem, so the results are a lot lower, but it does show some promising results. So for the DAL, again, kind of expected, just like task completion, it showed poor performance. It really can't learn from the input data well, and it really can't generalize well. But all the modifications I made to this network proved to be a better over the original network in task understanding. So it showed that removing the pooling layer, adding transfer learning, and using Bellman implementation showed to be a good improvement over it. For the DQN architectures, it proved to be, again, an improvement over the DAL architectures, or the DAL network by a good margin. The DQN-AL performed similar to the DAL. That was just because there was no target Q network used in there, because I wanted to see how well the DQN network did without a target Q network. And it showed that this network, again, the Q values fluctuate so much, the network ends up diverging. The scheduled shared experience, again, proved to be an enhancement. The dueling DQN showed to be the best performance, just like it did in task completion. And the DRQN performed the worst, again, as is expected, since this is not a partially observable environment, as well as the MDP rule, it doesn't follow. So some conclusions. So on my novel contributions, the reward abstraction, while small, allowed me to take the deep Q networks that worked so well in reinforced learning and bring it to the apprenticeship learning world, which hadn't been done. From there, I found the scheduled shared experience helps to guide the learning of an agent over time, and it kind of models our thought process as a human as we grow up from when we're young. The dueling DQN architecture proves to be really robust in apprenticeship learning. And again, it's kind of the standard in DQ networks in the reinforcement learning side, and hopefully become that network architecture can become the standard for apprenticeship learning. And the DRQN architecture, in the comparison, proves to be just too complex an architecture for this problem space. So some future work. Like I said, this is a research area that is continually evolving. There's not many people in the field, but the people who are in the field are producing papers and producing research at a pretty fast pace. Just this year alone, there's probably 6 or 7 papers on this, so I was like scrambling to figure out this research to put in my thesis. So one of the things that can be done is generating human data sets, again, which can be really timely. But you need to have these robust data sets so you can do a proper benchmark over all the networks. Another issue is that expert data, if you give somebody a video of you doing something or you're watching a video, it's usually perfect. There's not very many mistakes. There might be a little bit, but not much. And that can cause a lot of times overfitting. So how can we remove that stochasticity? A lot of times you can't control what the expert gives you or what videos you're watching, but you can introduce stochasticity in the agent learning. So you can say, with probability epsilon, we can use epsilon greedy again. I'm going to choose a random action. I'm not going to choose what the expert wants me to choose. And from there, you can explore different states and explore different ways of solving a problem and use the expert as almost just a guide. And then also, so reinforcement learning goes really, really well in Atari games, right? It's a controlled environment, you know the score, you know exactly what moves you're supposed to make, and it does really well there. But it doesn't really work well in real world applications where you don't know the reward structure. That's where apprenticeship learning shines. Bringing this to a real world where you say, well, I want to teach a robotic surgical system to make proper cuts. That's something that this system can do. So the next step is really bring this type of research into the physical world to see how well it does. Can we actually have systems learn and generalize a task just through expert videos? So that's the conclusion of my presentation. Again, thank you all for coming and listening. Any questions or comments or concerns you all have?